So yeah, let's go on. So the next part, I wanted to introduce explicitly these families that I just presented, the MPS and PEPs, which are sort of like the main ones, I would say, to do systematic study of quantum many-body problems. So let's start with the start of tensor networks, which is matrix states. So very simply, in the pictorial language that I introduced before, what you can think of a tensor network is a particular reduction of this generic state of the quantum many-body system to one particular ansatz. And in pictures is precisely, so we start with this general state that I've shown several times now, and instead of that, we consider states where the coefficients are given not by this general state, but by something that has the structure that is depicted here. So basically, you have a number of tensors. You see each tensor has just one leg, so it corresponds to one of the physical indices, and then it has two what we call virtual legs, the ones that are not open, that are connected to other tensors. We call them virtual. So it has two virtual legs that connects to the neighboring tensors, left and right. So this is the picture of a matrix product state, and it's called a matrix product state because if you look at the explicit form of the coefficients in the product basis, which is written here, what you have is that once you choose one element of the basis, so one value for each of the indices, that would mean that you fix the value of these open indices for each of the tensors. So basically, you don't have an open index anymore. So what you have for each of these tensors is an object with two legs. This is a matrix. So you have a product of matrices. So coefficients are products of matrices, hence the name. Okay, something interesting is that in the numerical, so in the applied mathematics community, this ansatz was independently discovered some years ago, and they call it a tensor train. So it's very graphical in my opinion, like that, right? So, okay, how many components do you have? How many parameters do you have in such an ansatz? Well, you just have to see that you have one tensor per side, and each of the tensors has these three legs. So the number of components is really taking the product of all the dimensions. So it's something that goes with the physical dimension. Now I'm introducing notation here. We usually denote the physical dimension, so this dimension of the individual bases as a small d, and the virtual dimension we denote with a capital D. That also changes depending on the papers and the family of tensor networks, but I will sort of try to be consistent with that. So the number of parameters that you have in this ansatz is really the product of this d, small d times capital D squared, n times for the number of tensors. So it's something that goes linearly with the system size. So this is like efficient. Something that also happens in this ansatz, and I chose not to show this explicitly, but I'm just mentioning it because it's very important, is that it has the area law built in. But the way to see it, without showing it explicitly here for lack of time, is really that if you cut your system in, say, you cut out a subregion in your system, say that you cut out these three sides, and the chain continues, of course, on both sides. This is just a piece of the state. Then the entanglement that you have between this piece and the rest is just mediated by these two bounds that you are cutting. And no matter how big your subsystem is, there will always be only two bounds. And as I said before, the entanglement is supported by the bonds of the tensor network. So in this case, it doesn't scale with the size of the subregion, so this is why you have an area law. Basically, because an area law in one dimension scales like the size of the boundary, which is constant because you have 1 or 2 points to cut out your subregion. Okay, so just let me show an explicit example, which is very simple, in case you never saw an MPS before. This is, I think, one of the simplest, and you wonder which kind of states can you represent in this way, with these tensors and so on. Well, one of the simplest examples that you could construct is something like this. So you have something of dimension 2, could be like spin 1/2 particles or qubits, 0, 1, for the basis. And then you have to specify tensors that have like 2 components for the physical dimension, and then some bond dimension. The bond dimension is a parameter in your family. You can choose something which is a product, would have bond dimension 1, wouldn't have any additional dimension. That would be the product state that I was showing before. The next thing you can do is something with bond dimension 2. It's like the smallest example. So I'm showing here one example with bond dimension 2. So bond dimension 2 means that these tensors have 2 matrices which are 2 times 2. One matrix for each of the component of the values of the physical index. So I'm showing just the explicit example here. This will be the matrix for value 0 of the physical index. This will be the matrix for value 1. And if you just take explicitly this product and see which components of the bases appear in this MPS, what you see is that this basically represents, over some details, but it's not important now. So this basically represents an entangled state, which is this kind of W state. Like you have a 1 in one of your sites, and exactly 1, and 0 in all the rest. Okay, so just a comment for those of you who are maybe are more familiar with these things. This is actually, you see that this MPS has a regular pattern in the components that appear. This is actually a fundamental property of MPSs. So they basically give you some kind of regular pattern in the components of your state. But I'm not talking about that for now. So this is just to show that a very simple example, going to D equal 2, gives you an entangled state with this very efficient representation. You just have these small matrices to represent it. Okay, MPS have a lot of properties that we sort of exploit for the numerics and that we exploit for understanding formally which kind of states are represented by them. I'm just showing some here and not the others. As I said, I'll give you some references at the end where you can read more if you are interested in these things. So one very important property is that we can compute expectation values efficiently. So what you want to do is to compute, for instance, in this example, you want to compute the contraction of a given observable in between the ket and the bra for the state. The ket of the state I'm representing with these upward-looking indices here in this picture as an MPS. The bra, as I said before, I now revert the indices. You understand that it's complex conjugate. It's not fundamental for the properties I'm mentioning. Now, if my observable is a quantum many-body observable, it's something that acts on all the sides in any arbitrary way, I haven't solved anything with this ansatz. I haven't gained anything because I still have exponentially many components in the observable that I will need to contract with each of the coefficients in my ket and my bra. Now, we are usually not interested in this kind of observables. We are interested in something which are local observables. For instance, we want to compute the magnetization somehow, or sums of local observables, or few body observables. Let's go to the single site observable, which is the simplest case. So we want to compute magnetization on this site. So now the observable is really the tensor product of identity everywhere except on one side where I have something else. And something else is a matrix which is 2 times 2. So basically it's this kind of little box. So my diagram now is very different. So now I still have the structure of the MPS built in. And now this means that I can compute this efficiently if I don't do the full contraction as is written in here, but I just do the local contractions first. So basically I go side by side, and for this side I will have like, if I contract these two things together, I will have a tensor that has 2 indices, and so on for the other sides where I will have some tensors in between that have a constant number of indices, so constant dimension. And now I can contract all these things. This is, again, a product of matrices that I can do efficiently. It will scale only linearly with the system size, but not exponentially as the general calculation did. So this is a very fundamental property to understand, to use these things in numerics, but also this kind of object that I'm showing in here. This is a very fundamental object in matrix product states. It's called the transfer operator. It's the contraction of the tensor, and it's adjoint for one side. I'm not talking much about this because I don't have time, but this is really an object that gives you the properties or many of the fundamental properties of an MPS. Okay, so in a very similar way, one can show that this ansatz has exponentially decaying correlations. Again, I have to do choose here what to show and what not. I'm jumping over this, but it's a very fundamental property because it really tells you that if you have a matrix product state with finite bond dimension, and you look at 2-point correlation functions, this is the expectation value of the product of 2 operators, but you are typically interested in looking at the connected component of that, subtracting the product of the individual expectation values to see if there is entanglement in your state. Well, this thing will decay exponentially with in the MPS. So it cannot really reproduce the behavior of critical correlations. I want to show some other properties that are more graphical, because this is like a lot of information, but as I said, things can be read in the bibliography later. Okay, so let me just check. One important property is that any state can be written as a matrix product state. And the way to do it, so the ingredients to do this I already showed in the graphical language, is just we have a general state, one in there, and we take a singular value decomposition of one of the physical legs, one of the edges, versus the others. And well, I showed you before how a singular value decomposition looks like. It's like putting an extra bond in between this part of the system and the rest, and I can continue doing the same thing. Okay, one thing that I jumped over now is this bond has a dimension, of course, is the number of Schmidt values, and because the singular value, the number of non-zero singular values is upper bounded by the rank of the matrix, which is bounded by the smallest dimension. If I have a rectangular matrix, the rank can only be as large as the smallest of both dimensions. Well, in this case, I assume that this is a large block, so the dimension of one side is smaller than d to the L minus 1 that are to the right. So I can say that the largest bond dimension that I can have in here is the same as the physical dimension. And I can continue doing the same thing, but now, of course, now I'm taking a singular value decomposition of this thing that is now a matrix, you see, that has indices, the product of d squared versus the rest. So it can be up to d squared. And so on. So I can continue doing this for all my chain. I can also start on the other side and do the same thing going inwards, just to get the bound at the first time. And if I do that from both edges, then what I see is that in the worst case, when I cut, oops, sorry, this I didn't want to do now. So when I cut in the middle of the chain, I will have like half of the dimension to the one side, half of the dimension to the other one. So the largest rank that I can have at all is the physical dimension to 1/2 of the size of the system. So basically, if I do this, I haven't cut anything, so this is exactly the state I had before. So with this bond dimension, I have enough to represent any state. And in that sense, they are a complete family. I can cover the whole Hilbert space with matrix product states. Of course, this bond dimension that I need is exponentially large with the system size, so I wouldn't have gained anything if I'm doing that, but it's an interesting property. Also, because there is a hierarchy in the matrix product states, so that if I start with bond dimension 1, I have the product states. But now I have these vectors, and I can always take this vector, which is like a 1 times 1 matrix, and embed it in a 2 times 2 matrix and put some extra parameters around. So the family with bond dimension 2 includes the one with bond dimension 1, and so on. So I can increase the bond dimension, giving the MPS the possibility to describe more entanglement as I make them bigger, and eventually cover the whole Hilbert space if I go high enough in bond dimension. So this is a very like condensed introduction to the properties of MPS. I didn't go over all of them. Let me just add here something that I'm not really discussing a lot, but which is also important. So I already described this property that is a complete family. I didn't show but mention that they have exponentially decaying correlations. It is also true that if we have an MPS, in principle, we have an efficient recipe to prepare it in the lab. So these are states that can be prepared efficiently. And well, I talked about the calculation of expectation values, and something that I didn't really talk about explicitly, but I was hinting to at the beginning, is that they are actually good approximations to ground states of local Hamiltonians. And this is more than just these intuitive ideas that I gave. This is like mathematical result, that this is really the set that describes ground states of local gap Hamiltonians, or states with ground states of gap local well finite range Hamiltonians. And this is very much related to this property that these ground states satisfy an area law of entanglement. So the next step is to go to higher dimensions. As David was saying before, you are not only interested in one-dimensional systems, of course, and in these quantum computers, really, the power is being able to go to higher dimensions, so other connectivities. So what about going to higher dimensions? Well, since I just told you that matrix product states are a complete family, the first thing you can think about is to use MPS, right? Because it's a complete family. It doesn't really matter that your underlying lattice is 2D or whatever geometry. You can put an MPS on top of that. So for instance, for the two-dimensional lattice, as it is here, wrapping it around the lattice. This people call as a snake MPS sometimes, and often refer to when people do 2D DMRG, or they call out DMRG. So, okay, now we have an ansatz to describe the state of this two-dimensional lattice. And the state of this lattice is, say, L times L. What happens with an MPS is that because it has this intrinsically dimensional structure, we can always cut the system in two by cutting one of the bonds, just one. The system has an area law. We expect the entropy for this partition scales as the number of links that we are cutting in this lattice. So you before actually because I jumped over it. The MPS has an upper bound. Upper bound by the logarithm of the bond dimension. Intuitive picture that the bonds support the entanglement. The way it's supported is with up to how big the dimension of the bond is, and the entropy that I can have is upper bounded by the logarithm of this bond dimension. If I have to support all this entanglement that grows with L in one bond, and I know that the entropy that I can hold is only logarithmic in the bond dimension, this immediately implies that to keep up with this entanglement when I make the system larger and larger, my bond dimension needs to scale exponentially with the systems. And exponentially, of course, is very bad for numerics. So this is something that we cannot do. We will be able to do it for small systems. People do it arranging the lattice allows them to do very precise calculations. Do techniques like finite size scaling, large is as we want. So it doesn't scale well. Very different from what happens to one-dimensional systems. So in one-dimensional systems, the MPS scales very well. So the natural solution is to larger dimensions or to arbitrary lattices, actually. And this is what a PEPS is. So a PEPS, which is shown in here, you see, is substituting the MPS, where we basically had one tensor. So this is a three-dimensional depiction of the tensors now, to make it clear that there are more dimensions now. Okay. And this gives me a construction, a tensor network. That I want. So this is precisely before, but now I have more virtual legs with this capital D, and the physical bond is still. Sorry, I'm losing this. The physical bond is still represented with. And this is what is called a PEPS. So precisely say the definition if you want. Do have an area law by construction, because now if we cut a region out of this two-dimensional lattice and check how much entanglement can we have in, I'm just talking very generally now and not showing the equations, but I told you that the entanglement is supported in the bonds, so I really need to count how many bonds I am cutting to separate this region from the rest. And the number of bonds I'm cutting is, of course, going with the size of the boundary. So area law scaling. Now they have other properties which are very different from matrix product states, and they concern actually for contraction, the computation of expectation values. So the simplest expectation value that we can compute is the norm, like the contraction of the state with its adjoint, right? So now you see, I changed the notation because this picture my kit is completely arbitrary. So if I want to compute the norm, I have to contract this guy with the bra, so the adjoint. Again, I flip the indices and assume that I'm taking the complex conjugate. So now what I need to do to take the contraction is to connect its index in the ket with the corresponding index in the bra. In the picture, this means joining together the physical indices now. So now you see I have like a two-layer PEPs with no open indices anymore. Right? So I can now flip it and look at it from above. Right? So if you remember the MPS picture that I had before, this is the same thing, but now it has 2 dimensions. Okay? So now this is my problem. So my norm is the contraction of this 2-dimensional tensor network. And now let's say that we try to do it in a similar way as we did for the MPS. So we look at a local part, we contract it together, we have a bigger tensor with like double indices everywhere. We could do this in every site, and we still have this structure of the PEPs. And now we want to contract everything together to end up in a scalar, right, which is the norm. Well, you take the first one, this would have dimension d squared times d squared, because these legs are now double, and then you contract a new one inside, and then it will have like d to the 4 times d squared, and so on. This is one way of doing the contraction. You can do it in any other way you want. The result is that at the end, the dimension of this that you are constructing grows as you include more and more tensors. Very different from the MPS, where you basically had these matrices and you can just take a matrix thing that will grow exponentially with the systems. Actually, this is a fundamental PEPs or generic PEPs cannot be contracted efficiently. The problem of contracting objects in general is Sharpie complete, which is very hard. It's harder than NP. So this is something that we cannot do. So how do we do numerics with them? Well, is to use approximations for the contractions, which actually can work quite well in physically relevant situations, because this is also related to the correlations that you have in your state. So for instance, in which if you want to contract this network, you can try to reduce one part of it to a one-dimensional matrix product state structure. And there are other techniques, but somehow this is deep at the that you so doing these approximations that they are called very fundamental to the numerics with PEPs. So PEPs have some properties that are similar to the MPS, but some that are very different. So for instance, we cannot compute expectation values efficiently, but on support much more correlations than matrix product states. And again, we know of very small PEPs with very small bond dimensions that can support algebraically decaying correlations, so really critical correlations. Not all states with critical correlations have this property, but have this. At the same time, even if we have small PEPs tensors, we don't have a recipe to prepare them. It's very big. And they are actually Hamiltonians, and we know the approximations to thermal states. But the properties are not so well understood or so not understood for states. Yes? Long range, one dimensional. Well, I mean, an MPS is an like how do you say? An instance natural. So if you an MPS is a PEPs. That's what I was gonna say. So if you do an MPS, you can say you're doing a family of PEPs. To put a two-dimensional ansatz for the long range, that's a bit strange. Okay, so you can say long range is not 1D. It has some more connectivity. Okay, I use a different graph and put a tensor network in there. The problem is that then you have problems contracting it. So it might be more useful for that. try to do that, but because typically when you say is 1D, the description is 1D. If you have a graph where connectivity is not just to two neighbors each, so it's really not 1D. And then you can use PEPs for this graph. Okay. And then we take a properties that tensor networks work very well with symmetries, and symmetries are very important if we want to study the physics of some problems, right? Invariant under some pin system, and it's invariant under, so it has, I don't know, conserved magnetization, so it has one symmetry. You can rotate the spins at once with the same rotation. Your model is invariant, so maybe you are looking for a state that also has the same property. But the property you are looking at is you have, for instance, a PEPs, in each of your sides, the same one. For instance, is unity to the number of sides. It remains invariant, so nothing happens. When you can construct a tensor network with that property, if your model example that I was showing, you can ask that each of the tensors transform with this in this way, so that basically you can apply the transformation on the physical index, and it's the same as applying transformations and its adjoints on the virtual indices. And if this is the property for all the tensors, and you do it in the translational invariant setting, of course you go back here, you apply this property, and what you see is that its transformation cancels with the adjoint. They all vanish, so your state is automatically invariant. So this is somehow one example of what I was saying before. You have these small local pieces, you impose properties on them, then you have states which have a global property. Matrix cannot leave. So if your state is invariant, you can find a representation that has this property. This is because you can work with tensors that impose the right symmetry, and it's very useful from formal side. So these are some references, but this is very which you can really understand the properties of states that you can construct with tensors by imposing or the symmetry properties of tensors. Symmetry properties of they have some kind of block structure. Some values of your indices are connected, so some others are not some arbitrary ones. I'm not talking about the details, but somehow this is the... And this also is also true for gate symmetry. So you can, I showed this kind of global symmetry. Of course, there are models where we have gate symmetry. Local transformations, we can do transformations in different sites. This is a gate symmetry. This also works well with. So I think this is again a good moment to a couple of minutes. Maybe you have some questions, and if not, yes, I wrote the acronym, but I'm talking too fast. You see, it means projected entangled pairs states. I didn't show, because I mean, lack of time, I didn't show you all the possible ways of constructing an MPS or a PEPs. A PEPs is just the generalization. But one way of constructing an MPS is to think that each of your sites contains two virtual particles. Each virtual particle is maximally entangled with one of the neighbors. So you put basically a maximally entangled pair along each bond in your lattice. And now you take a local projection of these virtual particles onto the physical degrees of freedom. So that's true for the MPS, but the acronym was introduced for PEPs, which, as I said, is a generalization. So MPS are a particular case where one of these do not exist. So this is these maximally entangled pairs that you put across each bond in your lattice, and then you take a projection onto the physical degrees of freedom. Okay, so back to the final block. So I want to talk about algorithms. So what kind of things can we do with these tools? And well, there are many algorithms. There are many works using tensor networks. So I'm simplifying the story a lot, trying to give you the basic ingredients in here. And I would say that the simplest story is that there are two main kinds of algorithms. So one of them is the variational optimization of an ansatz. Say we choose our ansatz to describe the state that we are interested in, and we optimize variationally some cost function. So typically this is used for ground states, and it's the basis of DMRG. So the like most successful algorithm for low-dimensional strongly correlated states. The other big group of algorithms would be how to transform one of these ansatzes when you apply on top of it some operator. It can be a local one or something the tensor network structure. And this is the basis of like the most used evolution algorithms. Although, well, some disclaimers are needed here. And also, it's like the basis of being able to do linear algebra in, say, the set of tensor network states, or the family that you choose. So it opens the door to do many different applications. So just very briefly, as I said before, the variational optimization, which is mostly used for ground states, is really sometimes used equivalently to DMRG, although there are some subtle differences. And the idea is that you use a variational principle, you minimize the expectation value, say, for ground states of the energy, over a family of ansatzes. For instance, here the picture is that of an MPS. So basically what you want to do is to minimize the expectation value of the energy, which would be the contraction of like one MPS, something in between, which would be the Hamiltonian or any cost function that has some kind of matrix product state structure. But the picture is sort of descriptive. And you want to, well, to ensure that the state is normalized, so you basically try to minimize this quantity. And the way it works is you optimize tensor by tensor, typically. So you fix all the tensors and optimize one of them. No details in here. So rather than the details, what I decided is to show you an example in case you never run a DMRG code. Simplest example, taking the Ising model in transverse field. And, well, I'm writing it here in a particular convention. We know this model is critical if like both parameters in this convention are 1. Okay? So what can we do exactly? Well, exactly we cannot do very large systems, but we could do something like 20 spins in a laptop in a little time. So it's something that you can just run in your MATLAB or Python code in like minutes. So the dimension of this system, so if it has 20 spins, is something like 1 million, 2 to the 20. And the maximum bond dimension that you require to write any state, as I said before, would be something like 1,000. So you can solve this. So for this example, I ran this some time ago in MATLAB. So I just use this AX function that you also have in Python and finds you the like lowest eigenvalues for a sparse matrix. So you construct the Hamiltonian, you run the code, and you find that the energy of the ground state per particle is this number in here. And it took, in my laptop back then, something. Now you do the same thing with matrix product states. So this is a screenshot of running one MPS code. So again, the times are not very significant, but it's the same system, same size. And what you can see here, I hope, oops, sorry. I have to go out. Let me just go back, sorry. This. Okay, what you can see here, yes, is that running with bond dimension 10, you already get a precision which is of, like, I don't know, 8 or something digits in this energy per particle. For this example, because you can run it exactly anyway in your laptop, right? But you can, of course, go to larger systems. So now you make the system much larger. You take 200 sites. The physical dimension of this Hilbert space is 10 to the 60. Of course, you cannot do that exactly. The maximum bond dimension you would require, 10 to the 30. Also, you cannot do that in any way. You can run the same MPS code and start with a very small bond dimension. And then you can see, okay, here I didn't write the exact solution, which is known in this case because this is exactly solvable. But what you can do in this code is to see how the result improves as you increase the bond dimension. And you can see here, say, okay, let me just, okay. You can see here that running with bond dimension 10 already has something like 5 significant digits or so converts, and then you can improve by increasing the bond dimension now to 20 or 30 or so on. And you can see how it is already very well approximated with a very small bond dimension. And the times this took is like, well, from less than a second to just some 10, 15 seconds for this. So this gives you an idea or a feeling. Of course, not all the systems work this. An idea of how powerful this can be if you use the right ansatz rather than doing the exact diagonalization of the system. Okay, fine. So the other set of algorithms that I mentioned before is that of applying an operator, changing your ansatz, and using this for something like could be time evolution or something else. This can be done in different ways. So if really we have a local operator, like is the basics of like the most used time evolution. Basically what you can do is say in the MPS picture you have your MPS, which here I'm just showing a little piece of the MPS because I'm applying something local, like a two-body gate, like you could do in a quantum computing simulation. Then if you apply this and contract this exactly, what you get is a bigger tensor now for two sides. And this bigger tensor doesn't have the structure of your MPS. So algorithm, what it does is to find something in the structure of the MPS that approximates this result. And basically what you have to do here is this singular value decomposition operation, which is very basic, all these algorithms, all these methods. This is basically TBD in 2 lines, in two words. This is not the only way, so you can apply something that has a more general structure, like an MPO structure. In particular, if you want to do this linear algebra, you will often find this kind of structures. And then what you can do is the same as I was describing before with this variational method. You can also try to optimize your ansatz to best approximate the result of applying some MPO, or in 2 dimensions, you could do the same thing in principle for PEPs, although it gets much more complicated, and do this kind of variational thing. As I said, this is the basic of the most popular time evolution algorithms. There are others like TDBP, if in this way, but it's like for like more specific, say, for a more specific talk, say. Okay, so time evolution is something very interesting. I already, Paula mentioned, I'm very interested in time evolution with MPSs, so let me just 10 minutes, 5 to 10 minutes, tell you why this is not so easy, what happens in here. So the basic algorithm that I was mentioning before, basically what it does, say in the one-dimensional case, would be to start with an MPS. This is the MPS. You want to apply an evolution operator, which, say, constant Hamiltonian is just the exponential of the Hamiltonian. Now this is a global operator. I said before, a global operator we cannot apply easily on the MPS. So the trick, the usual trick, is to break it in small pieces, so small time steps, discretize the time, and this is trotterization. Say, oh, well, not I went in that direction. So still, each of the pieces is just a small exponential of the Hamiltonian. This is still non-local. So we still. So the next step is to approximate these small steps as a product of local tensors. In particular, if you think in the quantum computation language, you could think of approximating it as a product of few body gates. In the case of a nearest neighbor Hamiltonian, then the recomposition is you have like even and odd gates that act on even links or odd links, and you can split your Hamiltonian in these 2 terms and approximate the action of one step, and this is really called the Suzuki-Trotter expansion, as the action of the even terms first and the odd terms later. The advantage of doing it this way is that within the odd terms, we have terms, for instance, that act on different links, so they do not overlap with each other, they all commute. And now this we can really apply all at once, or they have this kind of tensor network structure, because I would have something like this kind of brick wall structure. So this is not really an MPS MPO, but it's very similar, and actually I can rewrite it as an MPO by doing singular value decomposition. So basically the idea is that now I have an MPO approximation to one small step of my time evolution, and now what I want to do is to find an approximation of the result to this. As I said, there are different ways, but we know algorithms to do that. So I can do this truncating the bond dimension. I can repeat it for as many time steps until I reach the time I'm interested in. And guess for my evolved state. And now I compute observables in there. I said before we can compute efficiently. Now, this we can apply for time evolution, meaning that these exponentials can be e to the minus I t h for real-time evolution, but they could also be e to the minus tau h, right? So if I do imaginary time evolution, what I'm doing really is that, like this Euclidean time that people do in path integral, I'm trying to approach the ground state. So it's effectively projecting onto the ground state. I'm again skipping the details, but just showing a plot of what the results are. So what happens if you evolve in imaginary time is that your energy starts going down and it goes converging to the ground state energy. This is again the same example before, but now this is really the infinite chain. And if you look at how things converge when you change the bond dimension or you change the Trotter step, you see that in bond dimension, for instance, this curve contains 2 bond dimensions. This is very well converged already with a small bond dimension. And well, if you decrease the Trotter step, you get something better. But you can see that this is the error. So the error is really decreasing in the right way, say. It's converging to the right thing. It's a way to look for the way to thermal equilibrium, or the standard way. There are others. Now, if we do the same thing for real-time dynamics, this is again an example of the same model. You start in some initial state, which is a product. You switch on the Hamiltonian now, and measure one local observable, but after evolving in time. And now what you can see here is that the black line is the exact result, which for this case is known, and the color lines are the results that you obtain with increasing bond dimension. And you see that it is not converged. So it's converged for some short time, and then it goes completely crazy. You increase your bond dimension, you get a bit more time, it goes completely crazy, and so on. And this is of a real-time evolution. So what is the issue? Well, it's use entanglement, of course. The thing is that the entropy in this kind of situation can grow linearly with time. This means is that we will require a bond dimension that grows exponentially with time. So in this completely arbitrary picture, if I plot the bond dimension that I require as a function of time, and I put a cutoff in the maximum bond dimension that my computer can hold, what happens is that I put here this exponential curve. It will work for some short times, but after some time, it stops working because the exponential grows very fast and it goes over this cutoff. And if I double the bond dimension that I have, so I buy a more expensive computer that can do double the bond dimension, well, I can only gain a little bit of time. And this is what you saw in the plot before. I double the bond dimension, I only get a constant increment in time. The simulation of out of equilibrium dynamics is limited with matrix product states. We cannot do anything. So there are many physical situations. Also, I didn't talk about open systems, but they also are interesting and can be studied with these tools that can be studied with these things. For instance, adiabatic evolution, short times, low energy states. But the say key idea in this out of equilibrium dynamics is that what we can do with MPSs. And still, and this is coming to the open challenge here, many fundamental questions that we are interested in, and we would like tensor networks to help us understand. And these refer, for instance, to things as fundamental as thermalization. So whether or how a quantum system evolved out of equilibrium thermalizes. And let me just show this picture to basically finish. The, say, paradigmatic setup to study out of equilibrium dynamics is that of a global quench. So what happens in a global quench in 1D is that at time 0, you prepare your state in an easy state, for instance, a product state. This is exactly a matrix product state, it was shown in this picture. And then it evolves. At very long times, if evolution is generic, you expect things to thermalize. And what that means in this setup of closed quantum systems is that if you just look at local observables, they will look like given thermal ensemble. And we know that thermal equilibrium states are well described by a tensor network. In this case, it's a mixed state, so it's an MPO. I didn't talk about MPOs, but you see the picture. So we know that there is a description that gives us the local observables in an accurate way for a long time, or we expect so. Now, if you follow the evolution with this algorithm that I just mentioned, entropy grows linearly with time, the required bond dimension grows exponentially with time, and what you hit is what is called an entanglement barrier. You can go beyond sometimes. And so this is sort of the contradiction. We know what the state is at the beginning. We hope that there is an efficient description of local observables at the end, but we cannot follow the whole evolution of all the correlations. And this is somehow to go around this limitation, or at least bound it as much as possible to do as much as we can. With tensor networks, there's been recent progress. We are also working on that, and it's somehow one of the focuses of in particular, the problems I'm interested in now, tools to study these dynamical properties, which are not really following the full evolution. So this was just the last slide. To finish, just the 2 or 3 ideas that I wanted to transmit. Tensor networks are really this quantum-inspired tool for the classical simulations of quantum many-body systems, and they are based on entanglement. There are details. I forgot to showing at the beginning. There are some notes, the bibliography, if you are interested in. And there are many algorithms that are very useful, plenty of applications that you can see in the literature to find ground states, to find thermal states. We can do some simulations of time evolution, but they are limited. And the same happens for quantum circuits, as David was mentioning before. So these are out of equilibrium simulations where entanglement can grow very fast, and in principle, these tools have some limitations. However, this is there are very recent papers that have, motivated by the results of quantum devices, have really put a lot of work in optimizing tensor network to basically simulate the latest quantum computer results where they were claiming supremacy. The last one is the one that David was mentioning, this last reference of the simulation of the 127 qubits of IBM. So this shows you that these tools are really powerful. Of course, to do this simulation, just don't one of the existing codes of MPS and run them in your laptop. You have to put some work into optimizing things and thinking some smart tricks how to deal with these situations. But this shows you the power of. There is these open questions about trying to say something more interesting ones for physical properties or for physical problems. And just to finish, if you're interested in these things, because now we're all convinced that this is the thing to PhD positions available, so you can just contact me or write an email or. There is also the notes. The notes contain a more if you are interested, and yeah, if you still have. I mean, the one I'm aware of was from our group. So there was Ivan Glaser and Nicola Pancotti, Ignacio Cirac, somebody else. They did a more or less systematic study using some existing databases, comparing the expressivity of different tensor network ansatzes, not only MPSs, and restricted Boltzmann machines, and maybe some other neural network models. But I don't know. I mean, if there are other more recent works. So people have started looking at that. I don't, as far as I know, it's not that it's not the main stream connection that people are exploring between tensor networks, but there is something. So I would refer you to this reference. That is more sense. No, this was databases like pattern recognition. Okay, no. This is so. For instance, Giuseppe Carleo has done a lot of work on that, and so. Using like neural networks to describe like ground states of Hamiltonians. So there's been progress in 2D. There's recently something for time evolution. I don't know how systematic the comparison is, though. Yes. You can both do time evolution of like a mixed state in a closed system, so unitary time evolution. I mean, I didn't give you many details, but it's very similar to doing. Well, it's basically doing Heisenberg picture time evolution. So you can do it with the same algorithms, slight modifications of them that I showed. You can also look at master equations and evolve according to a master equation. This is, again, something that people have been have been doing for a long time. Well, Juanjo, for instance, has been working on this. And yes, indeed, that can also be done. Thank you.